2 days ago, the strongest open model in the world dropped. It beats models many times its size. Same brain as the version before it. Nobody retrained it. And it taught itself to hack. This is GLM-5.3, just released. And this is GLM-5.2, from the month before it. They are built on the exact same brain, the same base model, copied straight over. And the lab did not retrain a single weight of it. And yet the new one is the strongest open model there is, and the first to trade blows with the closed frontier. It keeps pace with the best closed models on real coding, beats them on a few tests, and at finding and exploiting real flaws in real software, it is more than twice as capable as the model it is a copy of. The program it came out of has already surfaced bugs hiding in code the whole world runs. One of them since 1981. Same brain, completely different model. So what actually changed? If you build with these models, you probably carry one simple rule in your head. Better model means bigger model. More parameters, more data, more months of pre-training on a bigger cluster. That is how we got here, and it is expensive, and it is slow. GLM 5.3 breaks that rule on purpose. The brain is frozen. Every single gain you are about to see came from what they did to the model after it was already built. They call it post-training. And here is the uncomfortable part for anyone paying for scale. A smaller, open model, trained better, just caught up to models many times its size. This release is a bet that the next stretch of progress is hiding in the training, not the size. So picture two phases. Pre-training is where the brain gets built. The model reads a huge slice of everything people have written, and it wires itself up. That part is finished. It is fixed. Post-training is school. You take that finished brain and you send it to practice. You give it a task, it attempts the task, and it gets a grade. Do more of what scored well, less of what did not. For 1 month, that is all this team did. No new brain, just school. More subjects, harder subjects, and far more time on the practice ground. But here is where it gets interesting for anyone who has actually tried this. When you train a model this way, the hard part stops being the model. It becomes the practice ground itself. They call each one an environment. And a good environment is not a quiz question. It is a real unit of expert work. Some of these tasks are days of work for an experienced engineer. Picture the model dropped into a real setup with a compute cluster, storage, internal docs, a live code base, and told, "This training pipeline is too slow. Find the bottleneck. Fix it. Run the experiments. Prove it is faster without breaking anything." That is the assignment. Not answer the question. Own the job. Now the catch. You cannot hand-build enough of those. You need thousands. And each one has to actually run. And each one has to be gradable, or the model learns nothing from it. So they taught the pipeline to build its own school. Research agents watch how real work gets done and turn it into runnable tasks with real dependencies and hidden state. Then a second agent tries to solve each one, just to prove it is even solvable. And the grader gets written without ever seeing the answer key. It only ships if it can tell a real solution apart from a no-op, and apart from a half-finished mess. Pass those checks, and you have a reward the model can train on directly. A school that writes its own exams and grades them itself. And the scores move the way you would hope. On Terminal Bench, a test of getting real work done in a real shell, GLM 5.2 scored 4.6. 5.3 scores 28. On a hard software engineering benchmark, 46 climbs to 67. And here is the part engineers should notice most. It got better and cheaper at the same time. On the lab's own coding benchmark, the new model solves more while spending fewer tokens to do it. 34% of tasks at 75,000 tokens each, where the old one hit 23% and burned 96,000. More done, less spent. And that stays true as you turn the effort up, which is not something even every big closed model can say. So where does that leave it in the pack? On the open benchmarks, this is the strongest open weights model for coding that exists right now. Against the closed frontier, it is mixed. On some tests, it slips past the big closed models while using less than half their token budget. On others, it is still behind the very top. Hold on to that one word, behind, because it is about to matter in a way the team did not see coming. They had added one more subject to the school. Security. Find the flaw in this code. That was the whole aim. Find isolated bugs. That is not what they got. As the training scaled, the model stopped just spotting single flaws. It started chaining them, planning across steps, reasoning about a whole path, from the first crack to a full break. Nobody trained it to do that. It emerged. It became the first open model to top a vulnerability discovery benchmark the closed frontier used to own. And on real exploitation, it did not inch up. It more than doubled. Then comes the line that should stop you. Across these security tests, the further up the chain a task sits, the harder and the more dangerous it is, the faster the model is improving. It is gaining quickest exactly where it is still furthest behind, which tells you the gap up there is not a wall. It is a countdown. So the question from the very start, how do you double a model's skill without changing the model? You do not touch the model. You rebuild the world it practices in. The ceiling was never the number of parameters. The ceiling is how real, how hard, and how plentiful the practice grounds are. Grow the school, and the same frozen brain keeps climbing. That is the whole idea behind this release. And it is why a capability nobody asked for, exploitation, showed up on its own. The moment the school got serious about security. And this is not a lab demo. Working with security teams, models from this program have already found 2,436 real vulnerabilities across 269 projects. Over 1,000 of them rated medium severity or worse. On average, each flaw had been sitting in live code for more than 26 years. The lab is publishing them as they get fixed, and it is holding the weights back for 2 extra weeks to harden the model first. Sit with that for a second. The people who built it need 2 more weeks before they feel safe letting it out. The weights come next, same frozen brain, and a school that now writes its own lessons. So here's what I keep turning over, and what we get into next. What happens the first time that school gets good enough to build a harder school than any human would have thought to?